most of the time, if you ask somebody what is the second law of Newton, they immediately say sum of the forces is equal mass times acceleration, but that is not exactly correct. So for us, since we are in a 200 level engineering course at a university, we want to learn stuff in more accurate form and more scientific, not just basically whatever that you can find here and there and just the common person knows. So what we need to know here is the actual second law of Newton is not F equal ma, it's sum of the forces is equal to time derivative of a quantity called linear momentum, and linear momentum is mass times velocity. It's a vector quantity, a scalar times a product times a vector, so m times v. And if, and only if, the mass of the particle does not change versus time, so the constant mass system, then you can show that sum f can be equal to ma, right? So again, the sum, the second law of Newton says sum of the forces is equal to d over dt of mv. Now here you have a product, so you have to apply the product rule. So it is going to be dm over dt times v plus m times dv over dt. And again, if m is constant and does not change with respect to time, then this guy is acceleration, right? That's derivative of velocity. Then we can say sum of the forces is equal to mass times acceleration. So for systems where this condition is not valid, you cannot use this format, you have to use this format. And you might say, where is it that the mass does change? Well, for many of you in the aerospace industry, that could be a rocket or a missile, right? Where the mass does change because a huge portion of the mass is the fuel, basically, in the thing that creates the thrust. So for many of applications, especially rockets and missiles, you cannot use F equal ma. You have to use some F equal d m(v) over dt. Now, in many textbooks, there is also a letter for denoting the linear momentum. There are different letters. Some textbooks use L, some textbooks use P. Okay, so some textbook says P equal mv. Some textbook might say L is equal mv. Okay, so anyways, it is a vector quantity. The unit of that is kilogram meter per second, or pound mass foot per second, and it is an important entity in dynamics. Now, should you have more than one particle, you have a system of particles, then you can still apply this equation, and here we assume that for a moment the mass of these particles that are in the system does not change versus time. So we're going to use the simplest version, the simpler version of Newton equation, sum F equal ma. If I apply this equation to each and every one of these particles, let's say a representative particle for all of these is m sub I, and r sub I is the position vector for that particle measured from the origin, and then the location of the centroid. You learn about centroid or center of mass in your statics. The location of center of mass of all of these particles measured from the origin is shown by r, or you can say r bar, doesn't matter. Now, each one of these particles is subjected to two types of forces. One is internal forces, the other one external So here F sub I superscript E is the external force applied to the ith particle, and Fij is the internal force applied from the jth particle to the ith particle. And since I have a bunch of those jth particle, if I want sum of all internal forces from all other particles applied to Mi, then I have to what? Sum all of those forces together. So this summation is sum of all internal forces on Mi. This guy is the external force on Mi, right? So this is basically the free body diagram of particle Mi, and this Ri is the position vector of it, right? So if I write my second law of Newton, this guy, for this particle Mi, what would happen? So it would be sum of all forces is equal to mass of this particle times what? Acceleration of this particle, right? But what is sum of the forces? Sum of the forces is sum of all those internal forces plus the external force. And for acceleration, I can write it as second time derivative of the position vector for this particle, right? So I can write it like this. You know, acceleration is second time derivative of the position vector, right? So for each I, when I goes from 1 to n, and n is the number of particles in that system, I can apply this equation, right? All I need is change I. Now, if I write this equation again for all of the particles and then sum all of those equations up, what would happen? So let's take a look. Here we start with a very simple case of just two particles. So here, let's say I have one particle here, one particle there. Okay, this is M1, this is M2. There is an external force on this one. I would call it F1 of E. There is one here. I would call it F2 of E. Then there is internal force exchange between these two guys. So this is F of 1, 2. This is F of 2, 1. And then the position vector of this particle with respect to the origin is called R1. The position vector for the other particle is called R2. And then the location of the centroid, so let's say this is the centroid. It is shown with R bar. Okay, so if I write second law of Newton for particle 1, it is going to be F1E plus F12 is equal to M1 d squared of R1 dt squared. And then similarly for particle 2, it is going to be F2E plus F21 is M2 d squared of R2 over dt squared, right? So these are the equations for these two particles. And now you might wonder what happens if I add these two together. What's going to happen? What do you think? So on the left side, you're going to get F1 of E plus F2 of E plus F12 plus F21 is equal to M1 R1 double dot, and I use double dots, instead of second derivative because they are the same thing. Just want to save some space. It's going to be like this. Now, the big question is, what is this second parentheses? It's sum of the two internal forces, one that is applied on particle 1 by particle 2, the other one from particle 2 to particle 1. What is the sum of these two? And you know from third law of Newton that these are action and reaction, and sum of them should always be equal to 0, right? Because for every action there is a reaction with equal magnitude and opposite direction. So F21 is negative F12. So when you add them, you're going to get 0. So, and this is what? This is summation of the external forces, right? On the system. Correct? Because these are all the external forces that you have from outside on the system. Now, what is this quantity on the right-hand side? M1 R1 double dot plus M2 R2 double dot. What is this guy? To answer this question, I want you to go back to the definition of the centroid. If I ask you what is R bar, or if you don't like to show it with R bar, let's show it with R of Cm. Maybe that is a better notation. RCm, what is that? So here, this vector, I would call it R of Cm, R of center of mass. How did we define it in our statics course? If you remember, it was M1 R1 plus M2 R2 divided by the total mass. Agreed? Therefore, if I cross multiply, I would get M1 R1 plus M2 R2 is equal to what? This is sum of all masses, right? It is going to be sum of all masses times what? R of the centroid. And now what I want you to do is to take a double time derivative from this equation. You would get M1 R1 double dot plus M2 R2 double dot is equal to summation of all masses times RCM double dot. And this guy on the left hand side is this one. So I can replace it here, right? If I call this equation equation 1 and I call this equation equation 2, from 1 and 2, I can see that sum of all external forces is equal to sum of the mass of the system times what? R double dot Cm. And what is R double dot Cm? That is the acceleration of the center of mass. So I would get this important equation, which looks very similar to the second law of Newton for a single particle, right? For a single particle, what we had was this, or a single mass, right? So you see, for a system, it looks very similar, except you have more than one mass, so you have to use the total mass here. And instead of, since you have several position vectors, you are not going to use individual ones. What you would use instead of individual positions vectors, because you have to use only one of them, it is going to be the representative of all, which is what? The position of the centroid. And then the most important thing is, among all forces that are applied to a system, only one category would create any effect. Only one category would create acceleration. And what is that? External forces. The internal forces do not create any acceleration for the centroid. Okay, so first, this is the summary of all I have done here in this slide, which is really important. And we have, I guess, written it in plain English. If not, it says sum of all external forces on a system of particles is equal to the total mass times acceleration at the centroid, or of the centroid. Okay? Now, two things we have to discuss, or at least provide some examples. One is, we said that only external forces do something. Let's look at a couple of examples to clarify that why internal forces don't do anything for the whole system. For individual ones, they might, but when you put the whole thing together and we squeeze all of the system in one single mass, call it, in one single point, call it the centroid, then the internal forces would have no effect on the motion of that point. So we have to talk about that, provide examples, and then talk about this acceleration. So let's take a look. First of all, why is it that these internal forces don't work? Probably you have experienced that, right? That if you are in your own car, right? If your car does not start and you're here, right? And you are really trying hard to start this thing, and it doesn't work. Gosh, my drawing is not really good. I don't know why I'm trying to draw, but please just bear up with me. Okay, maybe that's a little better. So now the question is, you are here sitting on a seat, right? And this seat is attached, of course, to the car. Now, here you are one mass and the rest of the car, all the car is another mass, right? So you are M1 and the rest of the car is M2. Now, if you want this car to start moving, what can you do? Can you push on the wheel? Probably when you were a child, you tried to push the car seat or the wheel to make it go faster, but it didn't, right? Yeah, I think I have done that too, and that is fine, because what you're applying, the force that here you're applying to this wheel, if we call it F of 2 on 1 from 2, then the car applies the exact same thing back to you. So if you look at this whole thing as one system, these two would cancel each other and they do not make these two to move. There should be something from external, from outside this car to make it move. And that's where you probably put your car in neutral and you ask your big friend and say, hey, could you come and push this car? If he applies some external force, then you would see your whole system, you and car together will move. Okay, so it's only external forces that provide any acceleration to the whole system. Now, that's one example just to clarify. The other thing is about this acceleration term. When we say acceleration, whether it's here or in the second law of Newton for a single particle here, this acceleration is measured with respect to what? Okay, that is really important, because we learned in the previous chapter in the relative motion that the acceleration, the velocity, the position that different observers report from the same object, from the same particle, could be different. depending on whether they move or not and how they move. So not always these numbers are the same. So from one train or one object or one airplane, there could be 10 different observers that are measuring its acceleration. A. Which one of those A's do I put in this formula or in the original formula? Okay, and again, these numbers cannot necessarily be the same. Let's look at some examples first to see why they can be different, although we have done it in the past, and then we come back to the very important question of which one would you put in the Newton's second law, because not every one of them is applicable here. So one example is this. If you are on a Ferris wheel or anything like that, or merry-go-round, and it is basically there is a person here sitting or standing, and it goes on a circular motion with a constant omega or constant v. And here I want you to look at two different cameras or radars or devices that are observing the motion of this person. The first one is also on the Ferris wheel, and it is doing the same spin that the person does with the same radius. Could you tell me what type of motion, what acceleration does this camera potentially see? Of course, this camera, it cannot measure acceleration, but what kind of motion does this camera observe from this person? Yes, the answer is none, because this person is always in the same position relative to this camera. And this position, the distance and the angle, does never change as long as they don't move on the wheel, they stay in the same place. This is not going to measure anything. This is not going to see anything. If it could measure acceleration, it would report 0. But if this camera is down here on the ground fixed, what do you think this guy, this fixed camera, would measure or would see as the motion of this object? Clearly, it would see that this is going around the circle. So it does see that this person is moving. And we know, and we have learned in the previous chapter, that if you are going along a circle, right? So if you are here and going around the circle with a constant omega, and this radius is r, then you have an acceleration, a normal, or we call it centripetal acceleration, right? Which is r times omega squared, or v squared over r. Now, how do these people describe this? So if I first, so this is the fixed camera, and this is the moving camera. So if I want to write the equation of motion based on what the green camera, the fixed camera, does see, what should I write? So from the view of the fixed camera, if I want to apply the second law of Newton, it says sum of the forces is equal to mass of the particle times acceleration of the particle. And let's say this mass is just m. Okay? Now, he knows that there is an acceleration. If I now look at the magnitude, This A is not clearly what? 0. This A is non-zero, and the magnitude of it is equal to r times omega squared. So since there is an acceleration toward the center, there should be what? There should be a force here applied to this particle. So if I draw the free body diagram of the particle, and I'm looking from the top, so the weight and the normal reaction of this disk are perpendicular to the board. The only thing that I can see on this plane should be a force toward the center, which I call it F. Okay, so it should be like here. And if I call it F sub n, because it's a normal or radial force, then in the n direction, if I write it, I see that the magnitude Fn is going to be mr omega squared. And what do I call this force? Yes, I call it a centripetal force. Where does it come from in real life? When you're standing on this disk and it is rotating, it is coming from what? Lateral friction. Okay, it is coming from lateral friction, the same way that a car goes around a traffic circle. What allows your car to go around traffic circles is lateral friction of your tire with the road. You're going to see later that your tire with the road, or your feet with, in this case with the Ferris wheel, there are two types of frictions. One are longitudinal, which in the beginning of motion provide you with angular acceleration or linear acceleration. And the second one is lateral, that allows this kind of circular motion for you to happen. So everything makes sense. We know there is a lateral friction force that makes this happen, and everything makes sense. Okay? Now, if we look at what the moving camera would see. So this is the moving one, right? What do you think the moving camera would describe? It says sum of the forces is equal to m times a. But this camera does not see any acceleration. So for the camera, for this moving camera, this guy is 0. Therefore, there should be what? No force acting on the particle because it doesn't have acceleration. But we know there is. We know there is this lateral friction. So how can it be that there is some force? This guy is still mr omega squared in magnitude, but there is no acceleration. So there is force, no acceleration. How can it be? That's where, because this moving camera is what we call a non-inertial reference, because this is a non-inertial reference or observer, it cannot validate the second law of Newton. From the perspective of it, the second law of Newton is basically violated. So in order for this person or this observer to make it valid, he or she or it will create or come up with an imaginary force which has the same magnitude mr omega squared, but instead of radially inward, it is what? Radially outward. And it says not only that friction force, lateral friction, which is mr omega squared, not only that is applied on the particle, there is the same kind of force, the same magnitude type of force that is applied on the particle, but radially outward. So when you add these two together, this guy is also what? So this is mr omega squared minus mr omega squared, basically. This is what? 0. But we know this guy, the guy just made up. This does not exist. What is the source for that force? Right? This force does not exist. We are just making it up to say that the second law of Newton is still valid. First of all, what do we call this force? That's probably what you heard a lot. And it is called Sentry. This is centripetal, right? This is called what? Centrifugal force. So it is centrifugal force. Centrifugal force is a non-inertial force. It's an imaginary force that does not exist. Okay? And we just add that to our observation to make it valid. Why? Because we started with a bad reference in the beginning, and so now we are trying to justify it. Okay? And this is not the single case that you see this type of observation. I'll give you another one. Maybe this is more clarifying. So again, here, let's say you're looking at the pendulum. So here you have a pendulum, and it is oscillating about a pivot point, right, with the constant omega at the moment. Or you are doing it, it's not even fixed to the wall. You have here the control, and you're trying to spin a mass around your finger or around the fixed axis, right? You have probably done this thing. And if you draw the free body diagram of this mass, and again here, I'm considering that this is happening on a horizontal plane, not on a vertical plane. So the mass is perpendicular to the plane. Okay, so this is a top view. This is a pendulum on a horizontal plane. If you look, the only force on the horizontal plane is the tension of the rope. That's all it is. And if you apply the second law of Newton in this direction, let's call this direction x, sum of the forces is equal mass times acceleration. And if you want, we'll see, you can apply the second law of Newton along one axis only instead of in general, and then take the vectors away, make it a scalar equation. So now, since this particle is going on a circle with a radius of L, L is the length of the pendulum, therefore the magnitude of acceleration is what? We know it is L omega squared, right? So now you say, well, the only force in the x direction is T, therefore you can find the tension in the rope. It is ml omega squared, and you call it the centripetal force. This tension is what makes this mass basically go around the pivot point. And if you have done it, so this is your hand here instead of the pivot, you know the faster you try to spin it, the bigger tension you have to keep in the rope to make it happen, right? Or the longer the rope is, or the bigger the mass is, you have to provide a bigger tension to keep the radius and the motion constant. Now, if instead of me getting my acceleration from a stationary observer, so this L omega squared came from what? Came from a fixed observer here, from a fixed reference frame, because it could record L omega squared as the acceleration. Now, what if I put my camera here on this rope or bar or whatever device that you want to call it. What if I fix it with respect to the pendulum? What acceleration does this camera record, if it could, for the mass? 0, right? Because the position of this mass with respect to the camera is always the same. So here you have to apply 0 in the mass, but you know there is a force applied to the mass, and that is tension. And you know the tension exists because it's clearly pulling your hand here on the other side. So the tension exists, but no acceleration. How could that be? So here, again, you come up with an imaginary force which is in the radially outward direction, and you say that force is equal to ml omega squared, and again, you call it what? The centrifugal force. And then you say, well, sum of these two is 0, so there is no acceleration. So you see, this is what we have to come up with or make up in order to say, instead of sum F equal ma, what you really do is this. So this is what you do when you have, for an inertial observer, for this inertial observers that we have seen so far, you say sum of F equal what? Ma. There is a force, there is an acceleration. Now, but if it is a non-inertial observer, and if that non-inertial observer does not measure any acceleration for which the A is 0, so not every one of them, but the one that does not measure any acceleration, for them you say sum of the forces, actual forces, the ones that you can see and relate to an actual physical object, minus an imaginary force, which is m times a, is equal to what? 0. And 0 means what? When sum of the forces is 0, means the object is what? In statics condition, right? This is statics when sum of the forces is equal to 0. So this is a force that you create, and this is a non-inertial force, like centrifugal force, for example, that you come up with and set it equal to 0. Okay, so hopefully I could clarify. Let me give you a couple of more examples, because this topic is quite important and I really want you to know this before we get into application of a ton of equations. So the other example is, again, when you are going around a traffic circle, okay? So your car is here. This is the top view of your car, probably, something like that. And you are here sitting in the car. And when you go around this traffic circle with a constant omega and with a radius r, especially if you are the passenger, you feel that you are being basically, it's like somebody is want to kick you out of the door, right? It's like somebody is pushing you out of the curve, out of the circle. So you feel like if the door was open and I did not have my seatbelt on, if this guy is going too fast, I would probably be kicked out of the car. And it is right, you could be kicked out of the car. But why? Is there somebody pushing you in this direction? If you look at the free body diagram of this person, is there somebody, some imaginary force, which we call again centrifugal force, is that there really to kick you out of the car? The answer is no. Why then do you feel that force? Because it feels really actual, real. So the reason is this. If you look at the car from the top, What is the force that allows this car to have a lateral acceleration of r omega squared? What is this? What kind of force allows this car to have such lateral acceleration? I just told you it is called lateral friction of the tires, F. And this force is typically big enough, unless the road is wet or the radius you are going through is really small or the omega is really big. This is typically well enough, and if you basically turn your wheels enough, force is typically enough for most of the applications to make what? To make this car go around the circle and get what? Because this is equal to mass of the car times r times omega squared, okay? So this acceleration of the car is that force divided by the mass of the car. And since this guy is typically big enough, it is well capable of providing r omega squared. Now, if I look at u as a separate mass, so this is u from the top, okay, and this is you holding the wheel, correct? Let's say these are your legs or something like that. Let's not do this. So what force allows you to go on the same circle and get the same acceleration r omega squared? You don't have tires, car does. So this friction force is applied to the car, not you. So where do you get such force to create such acceleration r omega squared? Where would you get that force? Yes, you would get it from what? A friction, a lateral friction, but that lateral friction does not come from the tires, it comes from the car seat you are sitting on, right? And typically, the friction between you and the car seat is not that big to give your mass such a big acceleration. So what happens is, you don't get enough acceleration in that direction that the car does. Okay? So the car goes with, let's say, 2 meters per second inward. The acceleration of the car is like 2 units inward, but yours is 1 or 1.5 units. And what happens? You're going to be left behind. And that's the feeling that you are being kicked out of the car. Now, if you use car seat, the tension of the car seat would help to give you the same acceleration as the car does. But if you don't, and you turn quite fast, then you cannot get the same acceleration that the car does, and since your acceleration inward is less than the car, it's like you are being kicked out of the car. Another feeling is when you nail the brake. What happens? You feel like you are being thrown in the windshield. Who is pushing you? Because ideally, when you nail the brake, right, so you are going this way, when you nail the brake, the friction is backwards, right? The friction is backward to stop your car. How come? What is it that is forcing you to go to what? To the windshield. What is this imaginary force that is pushing you to the windshield? What is that? Yeah, you might say again, it's an inertial force or something. Come up with some force. It's inertia or something that I hear some people say. Not really. Because when you apply the brake, this huge friction force that comes from the interaction between your tire and road will give this car a huge acceleration backwards. Let's say 5 meters per second squared backwards. But what is stopping you? Because you were going with the same velocity that the car does. Now what makes you stop? This friction is not applied to you, it is applied to the tire of the car. What is that? It's again the friction between you and this car seat. This time in this direction, right? You want to move, I'm sorry, in the backwards direction. You want to move with respect to the seat, because the seat, which is attached to car, is slowed down, but you still keep moving. Nothing is stopping you. So the relative motion between you and the car seat is forward. Therefore, the friction applied from car seat to you is what? Backwards. But this friction is typically not huge to get you a huge backward acceleration. So your acceleration will be something like 3 units. And guess what happens? The car is moving backward a lot faster and with a bigger acceleration than you, so you're going to be left behind, therefore you go to the windshield. And the exact opposite happens when you start the car with a huge acceleration. The car gets a huge acceleration from the friction of the road, but you only get a smaller acceleration forward from the car seat friction, so you're going to be left behind in the forward direction, and that's like somebody's pushing you back to the car seats. So the only way that you can create such acceleration as the car has for yourself is to get help from the seat belt, because your friction with the car seat is not enough. That's why you should wear the seat belt in all sorts of situations. So hopefully I could clarify this. Now, going back to the main question I asked, when I said sum F equal MA, this A is with respect to what reference? What reference is allowed to report its recorded acceleration without forcing us to come up with all sorts of imaginary forces to make second law of Newton valid? Yes, this acceleration should come from what? An inertial observer. And you might ask, what is an inertial observer? It is an observer that does not have acceleration itself. So if your observer does not have acceleration itself, the number that it records is valid. Clearly in this case, you see this camera does have the centripetal acceleration itself. So the number it reports is not valid. Now, let's go back to this, because this is quite interesting. So it says it does not have acceleration. So what kind of observers do not have acceleration? Well, you might say one that is fixed. And then I ask you, fixed to what? And you might say fixed to the earth, fixed to the ground. And then again I come back and ask you, is earth fix itself? So that when you fix something to it, it's fixed. And you might say, well, not actually. Earth does have the spinning motion, right? When you are on the earth, so this is the earth, and you have North Pole and South Pole, and you are on some circle like this at your altitude, and then you're going around the circle, right? With some omega. So since you are here and moving with the earth, clearly you're going on a circular motion. And we know anything that goes on a circular motion, even with the constant omega, does have centripetal acceleration. In this case, toward the north-south axis, you have such acceleration. So really, Earth is not completely fixed. So now we go to this question. Why do we use it? In many applications, you see, we use the cameras, radars, all sorts of things that are attached to the Earth. Are they really valid? The accelerometers, all sorts of sensors. Can we really use them? Especially when they report acceleration. Well, the answer is for many daily applications, this centripetal acceleration of the Earth, even at the biggest circle at the equator, right, where you have R max, this is the maximum acceleration that you can have, right? Because if you remember, this is our omega squared, and omega is constant, so max acceleration centripetal happens at the equator. Okay? And if you calculate it, the radius of the Earth is about 6,300 kilometers, or 6,300,000 meters. And what is omega of the Earth? It is 2 pi radians, or 1 full revolution, in how many hours? 24 hours. And 24 hours is how many seconds? 3,600. That is the omega of the Earth in radian per second. And when you do this, it is about 0.02 meters per second squared. But what is the gravity G that most of our daily applications are under? This is 9.81 roughly, right? Depending on the altitude, but something in that order. So you see this number is significantly smaller than gravity, okay? It is less than what? It is less than 0.2 or close to 0.2% roughly. It's less than 1%. And am I correct? This is 10. 1% of 10 is 0.1, and this is 0.02. Yes. So this is 5 times less than 1% of G. Therefore, it's not really going to do anything. Not going to do anything, it does, but depending on how much accuracy you need in your application, it might be well sufficient. So if you go in our lecture, this important question asked that, can we use the Earth and any frame attached to the Earth as inertial for daily applications? And the answer is basically because of the small omega, for many applications, even for many missiles and flights, you can still use the Earth reference frame. Okay? So, although some other applications use distant stars that almost do not seem to be moving from us, they use those as reference, but for, as I said, many real applications we use a fixed reference frame attached to the Earth. So that's one thing that we had to discuss. The other thing, it says it does not have acceleration. What if it does have velocity, but constant velocity? So if my moving reference frame has only a constant velocity, okay, it's just going back or backward or forward only in one direction with a constant speed and does not change it, it means it does not have acceleration. Can we trust the measurement of that? And the answer is yes, you can, because the acceleration of that is 0. So no acceleration does not mean no motion. It could have motion, but it's a uniform motion. Okay, I guess now I discussed this topic in detail and could clarify everything. Now that we know it, let's go and see how we can apply these equations to Cartesian case, and there are two problems in our lecture. One of them, this one, the star problem, we'll leave for the classroom. But this one, this example 14.3, we're going to solve right now. So when you apply the second law of Newton, F equal ma, remember that we can decompose our force and we can decompose our acceleration along any set of axes or any axis that we want. Okay, there is no limitation, because this is a general rule that does not depend on which coordinate system you choose. It is valid regardless of what reference you choose, as long as it's inertial. And here we typically use fixed references. So we can decompose our force or our acceleration on any axis that we want. And well, one of the well-known cases is we can apply it along x, we can apply it along y, and along z. And if you do that, then you get sum of the forces in the x direction is max, sum of the forces in the y direction is may, and sum of the forces in the z direction is maz. So you get from one vector equation, you get how many scalar equations? 3. So this is one vector equation in 3D space, leads to what? 3 scalar equations. If it was written only on the xy, on the space that is 2D, then I would get 2 equations. But in general, for a particle motion translation, I have 3 equations, which you can see over here. Now, if along any of these directions the object does not move, it means the acceleration on that direction is 0, so I get static equations like this. So very simple, looks like what you had in physics, but now we want to apply this to this example 14.3, which is a nice example. And again, it might look like some of the problems that you have seen in the past, which you probably did, but we want to go in detail and discuss this nice example. So it says the two boxes start at rest. Means what? Their initial velocities are both equal to 0. That's the meaning of rest. The mass of A is 40 kilogram, mass of B is 30. The coefficient of kinetic friction is 0.15. For static friction is 0.2. What is the acceleration of the crates when you let them go? And then after 5 seconds, how far does box B go down or decline? Okay, so let's see what we can do. So whenever we solve any kinetic problem, these are the steps that you have to take. So please take a note of that and always follow these steps whenever you do any kinetics problem. First of all, not only for kinetics, for kinematics, write down what you have and what you are about to find. So I know MA is 40, MB is 30. I know mu K is 0.15, mu S is 0.2. Velocity of object A at the beginning is the same as velocity of object B in the beginning, and that is 0. Right? These are the givens. Then I want to find acceleration of object A, acceleration of object B after release, and then I want to know at t equal 5 seconds how much is delta y of object B. So first step, write down what is given, what you need to find out. Step number 1. Step number 2, draw a free body diagram. Draw a free body diagram. How many? As many as the object with masses. Here you have 2 masses, so you need 2 of them. Important thing is, if any of the objects are rotated, like this object A, do not rotate them back and make them horizontal. Do not. Always draw the free body diagram of all objects in the same orientation that they are. Okay? So you would leave object A rotated and object B like this. Same orientation. So again, do not rotate or change the object orientation when drawing a free body diagram. Let me write it somewhere because it is so important to me. So please do not alter the particles orientation in free body diagrams. Do not do that. Never ever. Because I have seen some students do it and then they make a bunch of mistakes. They forget to rotate the forces as well. And that is trouble. So now, draw the forces on each one. Cut each object separately from the rest of the word and only show the effect of those objects on this part. So for part A, we see that there is a contact. Any contact in real world comes with 2 forces, a normal force and a friction. So object A has a normal force and a friction. And then, of course, they have masses. Their masses are not negligible, so every object is under gravity. And then, of course, there is this rope which provides tension. Now, the direction of gravity is obvious. It is downward. What about the direction of the tension in the rope? It is along the rope, and force of a rope is always pulling. It's never pushing, so it is always pulling the object. It is never inward or pushing. It's always tension, not compression. If you make a mistake in this, you're going to end up with wrong results. The normal force is clear. It is normal to the direction of contact, which in this case is the inclined surface. Now, friction is what? Friction is parallel to the surface, like this, but the question is which one, upward or downward here? And we know friction is always opposite to the potential or active direction of relative motion between the 2 surfaces. And the question is, which direction does object A move with respect to the inclined surface? Well, if we go by the problem question, it says object B is going down, so A has to go down, therefore the friction is upward. But how does the problem know that this object B declines? Is there any way that the object B goes up and A goes up? No, of course not, because we know the tendencies of objects is to go down in elevation if they can and lose their gravity potential. Here, there is really no force from outside of the system to push it upward. There is nothing. If there was a person holding another rope and pulling, yes, that person could probably overcome the friction and the components of gravity. But in this case, there is no such a thing, so they have to go down. So therefore, the friction in this case is upward. But not always. Remember, not always it is that simple. Sometimes you have to do some analysis to make sure this friction is in which direction. Now, in this case, actually, there is some point to think about. How do we know the system even starts to move? Because we start from rest. You don't have any initial momentum. How do you know the system can move? Maybe the friction is too big here that the two components of the gravity of this guy and this guy is not capable to overcome that. Therefore, it stops. Especially A is heavier than B. It's 40, that's 30. So maybe the system never starts to move. If that's the case, then the answer to the acceleration and the displacement of B is both 0. So first, we have to find out whether this object B does really move down or it stays in place. And that's where I have been given both static and kinetic coefficients of friction. That's why mu s is given to you. Because if they move, all you need is mu k. Why mu s is given is for you to investigate whether they move or not. And so we have to check on that. And we will. So for the moment, let's say they are going down. So this is the FBD on object 1, or A. What about object B? Of course, again, there is gravity here, mb times g, and then the very same t upward. Make sure you do not create a new variable. This is action and reaction. These are the tension on the two sides of the rope, and they are the same thing. Again, not always tension in a rope on two ends is the same. There are some conditions for it to be valid, and I would mention that as well here. But object B does not have any contact with anything else, so that's good to go. So the first thing was, again, we draw FBDs. I would recommend that you name them. So I would call this FBD1, and I call this FBD2. And then I also need a coordinate system. So in the next step, before I can write any equation of x or y or whatever, I need to provide the meaning of x and y. So I need to show what is x, what is y, and that's a separate discussion. So before all of these questions pile up, I would like to go and clarify. First, let's find out why the system moves down. Let's talk about that. How do I know? So this is how you can find out. So if you combine these two objects together, okay, that's another way to draw a free body diagram. And actually, in this case, it is preferred over individual ones. So one way that you can act when solving dynamics problems for a system of objects is you combine the system into one single object and draw the FBD for that. So let me call this FBD3, if you don't mind. And I want to show the forces on this FBD. So here, this is N, this is F, this is MAG, and this is MBG. Where is T gone? T is the internal force in this system, and it is going to be cancelled, right? Because here you also included the cable as a part of the system, and this cable is massless, so it's not going to add to the mass of the system. But this cable, if you drew this cable also, which we don't need in this case, it had a tension like this on this end, and it had a tension of this like this at this end. and this two action and reaction would cancel, and this two action and reaction would cancel. So there will be no T. T is an internal force, and remember, internal forces do not contribute to the motion of a system of particles. So T is gone. That's the good thing about combining, is because this T, we don't know how much it is, right? So it is one unknown added to the rest of unknowns. And the more we can eliminate unknowns in solving dynamics problems is better. Always come up with FBDs, with situations that you have fewer unknowns in them. That makes solving problems extremely easier. So now, the question is, if this system wants to start moving, what is the force that makes the system move in the direction that it wants to move? Well, object B has this much of force to move it in the direction that it wants to go. What about object A? Object A wants to slide down the incline. So I have to see how much of force is driving object A forward. And clearly, if we know this angle here between MG and the vertical, this angle is the same as what? The incline angle, which is 20 degrees. So that angle is 20 degrees, and therefore this force is MAG sine of 20. This force in green wants to make A go down the incline. The other component, this one, which is MAG cosine of 20, this is what will be balanced out with N so that this object does not get off the surface. So if you look at all of the driving forces, all of the forces that want to move the system forward, so some of the forces that drive the system forward, in this case it is equal to MBG plus MAG sine of 20. Now, what is some of the forces that want to stop this system from moving forward? Clearly friction, right? So some of the forces that stop the system is F. When is it that the system does move? When the top force is bigger than the bottom force. Under that condition, the system moves. Now, what is the worst case scenario? The worst case scenario is when this force is the maximum that it could be. And we know the maximum friction that a surface can generate, right? F of max, friction of max, which is also the maximum static friction when the system does not move, or it's at the edge of moving, is equal to mu s times n, right? That's the capacity of the surface for generating friction. It can never go beyond this, and it never can generate friction above this. And in this case, if I knew n by multiplying by mu s, I could tell how much friction I can have. But it's not hard. If I just look into this direction, normal to the surface, so if I call this direction normal to the surface, if I call it like y prime, or if you don't like it, I can call it y1, or whatever you want to call it. In this direction, parallel to the inclined surface, I call it x1, okay? if I write sum of the forces along y1 direction is equal to mass of object A times acceleration of object A in the y1 direction. Clearly, object A does not get off the surface, so this guy is 0, and from here you see that n should be equal to mag cosine of 20, right? That's your static. And if I calculate this number with ma being 40 and g and cosine 20, so 40 times 9.81 times cosine d of 20, it's 368.74. 368.74. That's the normal reaction. Now, if I multiply that by a 0.2, which is mu s, that is gonna be max friction. So I multiply this by 0.2 and I get 73.75. So this is the max resisting force I can have, which does not want the system to move. But what is the force that wants to move the system? I have to say mbg plus mag sine 20. So I have to get this mag sine 20 plus what? mb, which is 30 times g. Clearly, you see that's a huge force. 428.51. So this is way bigger than this 73.75. Therefore, the system will start to decline. Okay, so you have to do this analysis first to show that this system will go down. You have to do that. Otherwise, you cannot confirm. So fine. First, now I know it does move. Good. And the friction is upward. Good. So we know this. That was the answer to the first question. Now what? We have a couple of more things to answer. I said, now you have to have coordinate frames. Let's look at that. So let's look at the coordinate system. And here I want to go to a next page and do the job one more time because it is getting too big and too much out of control. So I would rather show the free body diagrams and everything over here one more time and do a cleaner job. So this is N, this is MAG, this is T, and this is F. And this F is F sub K because we know it moves, so it's kinetic friction. This is the same T. Again, why is it the same T? I'll talk about it. And this is MBG. And I call this FBD1. And I call this FBD2. Now, the question I have is, what coordinate system do I use? Well, the only one so far we have discussed is rectangular. But which direction is good for rectangular? Do we go with traditional x and y? So do we use the traditional x right positive, y upward positive? Well, for object B, it definitely works because T and MGB are in the y direction, so I do not have to decompose any force. It's perfect. But if I use the same coordinate frame for object A, what would happen? The only force along one of these two traditional x and y is MAG. N, T, and Fk, they all have to be decomposed. Okay, yes? So N, T, and Fk, they all have to be decomposed along x and y. And not only that, actually worse than that is when for any of these objects, for this one, I'm sorry, for object A, if I say sum of the forces in the y direction is MAY, is AY of object A 0? No, because object A, as it declines the surface, it moves both to the right and also what? Upward, downward. So AY is not 0, and when I say sum fx for this object equal MAX, is AX equal 0? No. So none of this is equal to 0. They are related to each other, okay? They are related to each other. I can say AY over AX is tangent of 20 degrees. Fine, but I still have to decompose Tn and Fk with their sine and cosine components along x and y. So it makes it a little harder to solve. Instead of that, what I would do is for surfaces that are tilted, like inclined surface that I just have here, I would use a rotated version of coordinate frame. And I'm not going to call this new coordinate frame, I'm not going to call it xy again, because the x and y are different than here. So I would call them something else. I call this maybe x prime, y prime, or x1, y1. Okay, so can I use two different coordinate systems in the same problem? Yes, you can use as many as you want. Okay, Cartesian does not always mean traditional xy. You could rotate it. As long as you have three vertical axes, three axes perpendicular to each other in a right-hand manner. So do not limit yourself to one coordinate. For each particle, use the coordinate frame that is better for it. Now, in this case, there is no acceleration in y direction, in y1 direction, because the particle will never leave the surface, and plus N, T, and Fk are along x1 and y1 force axes. The only thing that you need to decompose is mg actually. So it makes it significantly easier. And now let's do it. So I say for FBD1, sum of the forces in the x direction, x1 actually, is equal to what? What forces do I have in the x1 direction? I have positive T, I have positive T, negative Fk, and then a component of mg. And if you remember from my previous explanation, this component of mg here that is parallel to the surface is mag sine of 20, and this component here that is perpendicular to the surface is mag cosine 20. So it is going to be plus mag sine 20 is equal to mass of the object times acceleration of the object in the x1 direction. And then sum of the forces in the y1 direction, which in this case is n minus mag cosine 2n, is mass of object A times acceleration of object A in the y1 direction. Then I applied the same equations for free body diagram 2, with the difference that in free body diagram 2 there is nothing along x, no motion, no force, nothing. So we get 0 equals 0. So all we need is just say sum Fy is, in this case, it is T minus mbg. This is equal to mass of the object times acceleration of the object in the y direction. Okay, so you have 3 equations. Now, do I have, that's the next step you have to do. Do I have enough equations? In order to determine that, I have to mark down the unknowns and knowns. Clearly, I don't know T. What about Fk? Since it's kinetic friction, it should be equal to what? Mu k times n. So it's not a new unknown. If I know n, because n is an unknown, I would know that. What is A of x1? That's clearly one of the unknowns of the problem. I don't know. And I don't know. What about A of A in the y1 direction? We said it's not going to get off the surface, so this is 0. Therefore, from here, I can find n, and it was what? mag cosine 2n, and I guess we found that number, and it was 368.74. Good. So we found n, but this equation is gone. So I found n. So I know mu k times n now. And in the third equation, again, it's the same t, not a new one, and aby is another unknown of the problem. So if I look now, I really have equation 1, the top one, and equation 2, the bottom one. But I have 3 unknowns. I have the accelerations, and I have t. And of course, you cannot solve for 3 unknowns out of 2 equations. So your kinetics at this point is dead end. You do not have enough equation to solve for all unknowns. And again, I write one of my other important notes that whenever kinetics is dead end, which means you cannot get enough equations, go back to kinematics. Go back, see if kinematics can provide you with any hint. Maybe it can give you one of these unknowns or relate them somehow to each other and give you one more equation. And yes, it does. Why? Because these 2 objects are connected by a rope, and this rope cannot be stretched. Therefore, this object in the x1 direction and this object in the y direction, both along their direction of motion, they have to use the same amount at the same time. Otherwise, this rope is going to be what? Stretched, which it cannot, or it's going to be compressed and it's going to lose its tension, where T is going to go to 0. So if we want to maintain this tension, we have to have what? AB in the y direction should be the same as AA in the x1 direction, because the 2 objects are connected by a rope. They have to move the same with the same acceleration. And now, if I combine 1, 2, and 3, I have 3 equations, 3 unknowns. I can easily get all 3. All I need to do is to subtract 1 from 2. If I subtract 1 from 2, the t is going to go away. So I put this 3 back in 2. So I'm going to put this in 2. It gives me t minus mbg is going to be mb times And I would call both of them A if you don't mind, since they are the same number. So it's going to be MB times A. And this is equation 4. And now this is also going to be A. And now I combine 1 and 4, which basically means subtracting them to get rid of T. Because T on the left side of both equations has a positive sign. So by subtracting, I would eliminate T, right? Look at 4 and look at 1. If I subtract the left side, I would get what? I would get negative Fk, which is negative 0.15 times N, so 368.74. Now let me write it, it doesn't matter. So mu k times N plus mag sine 20 minus, or let's make sure, negative Fk plus, so negative of that is going to be plus mbg is equal to ma plus mb times a. And here I have everything in this equation except for a, therefore I calculate a. Right? Because n is calculated, everything is calculated. Therefore, I'm going to get 5.33. This is the acceleration of both blocks and answer to part A of this problem. By the way, when you're looking at this equation, you might say, didn't I get this equation somewhere? Or could I get this somewhere? Yes, you could. If you looked at the free body diagram of the entire system, right? Where you have this Fk, and then N and mag, and then mbg, and T was internal force. If you look at this and combine these two masses into one mass, so you consider both of this is a system, consider it one mass. How much is this mass? Ma plus mb, which is moving with some acceleration a, and the forces that make the system move in the direction it wants to move is mbg plus the component of mag, which was mag sine 20, if you remember, and Fk is the one that doesn't like it. That's why it's negative, these two are positive. So yes, I could get this whole thing by just looking at the combined FBD. But the question is, this acceleration or these forces are along which axis? Because clearly mbg and mag sine 20 are not along the same axis, and acceleration of them are along different axes. So if I want to get this equation from the second law of Newton, I should write the second law of Newton about which axis. Remember, I said you can write your equation along any axis, but in this case, this axis is not x, y, z, or x1, y1, z1, or any of those. What is that? We're going to see it in the next lecture. It is in the tangent direction of the path. So this is f, some ft, t tangent direction is equal to m times at. So you could do that too and get to here before even the need to look at t. You could do that when the two particles move with the same acceleration, and you could combine and get rid of the internal force. Okay, so this is the answer to part A. Now it says after 5 seconds, how far does object B go down? So object B is showing a constant acceleration, and I know initially V of B at the beginning is 0. A of B is 5.33 in the downward direction. And I want to know at t equal 5 seconds how much this object goes down. And all I need, since this is constant, I would use the formulas I learned in chapter 13, where it says delta S is what? V naught times T plus 1/2 A times T squared, right? That's all I need. In here, since this object is going down, this delta S is going to be the same as what? Delta Y of B, and this is going to be V naught of B, and this is going to be A of B. So you just plug in the numbers. This is 0, this is 5, this is 5.33 over 2 times 5 squared, and you are going to get I don't see it here, let me get it. So 5.33 times 12.5, 6663. This is how far object B would go down after 5 seconds. Okay, so the problem is solved. I know we have gone a few minutes above our lecture time. You know, in some of my lecture stops and ends before 90 minutes. In some, it might, in a few actually, it might go a few minutes above. So hopefully when you average all of them, on average, I never go above 90 minutes. And I just want to clarify one last thing, and that is, if you have a rope, okay, and if I apply a force F on this side, and then on this side it is basically towing an object, I know it is going to apply a force T to the object on this side, and the reaction of that is applied to the rope itself. So the tension on this side is F, the other side is T. The question is, under what condition T is equal to F? Is the tension, or if I cut the rope here and look at the tension here, and I call this like T prime, is that also equal to T prime? Is the tension always the same along the rope? The answer is no. Hopefully you learn in statics that in order for the tension of the rope to be constant along the rope, you need two conditions. One, the mass of the rope is negligible, and two, there should not be any tie or knot along the rope. If it does, it's going to change the tension. So you need at minimal these two conditions for the tension of the rope to be all equal along. If the mass is not negligible, if the mass of the rope here is not negligible, what do you think would happen? If that's the case, I encourage you to see that if this is the case, then F is going to be bigger than T prime is going to be bigger than T. As you move along the rope, you're going to lose tension because a portion of it is used to accelerate the rope. Okay, so hopefully you'll know this as well. Thank you so much for your attention, and I will see you in the next lecture and in classroom.